So I'll quickly write down h1z. h1z that we have considered is nothing but z inverse into z plus half, which can be written as h1 of omega equal to e raised to minus j omega into e raised to j omega plus half, which is further e raised to minus j omega into e raised to j omega will be nothing but cos omega plus j sine omega plus half. So this is my h1 of omega. So what will be the angle of h1 of omega? The angle will be nothing but, because two terms are multiplied, the angles will be added. The angle of the first term is nothing but minus omega plus the angle of the second term. Second term is a complex term in rectangular form, for which angle is given as tan inverse of imaginary upon real part. Imaginary part is sine omega and real term is half plus cos omega. So that's the angle of h1 omega. I request everyone to go through the similar steps and write down angle of h2 omega. So similarly, angle of h2 omega will be nothing but minus omega plus tan inverse of, there will be a small difference, it will be sine omega 2 plus cos omega. That's because of the difference that 0 is inside the unit circle and outside the unit circle. So these are the phase spectrum that we have got. So the magnitude characteristics are identical because the zeros are reciprocal. Please note that whenever zeros are reciprocal, minus 2 and minus half, the magnitude spectrum of two systems will be exactly same. So if I now plot the phase spectrum for both the systems one by one, for the first system, if I plot the phase spectrum, it will look something like this. It will increase and pass through 0 and then again go down to 0. So this is the spectrum from minus pi to plus pi. This is the spectrum of the first system, phase spectrum of the first system with respect to omega, of course. And for the second system, if I plot the phase spectrum, angle h2 omega with respect to omega, then one observes that. So how do you understand that it goes through 0? For the first system, if I put omega equal to 0, then we get sine of 0. Now tan inverse of sine 0 will give you 0. Cos of 0 is 1. So the denominator becomes a non-zero value. So tan inverse of 0, and this is also 0, so it passes through 0 here. But you have to understand that when I take tan inverse of omega equal to pi and minus pi, so if I put omega equal to pi, then omega equal to pi, sine of pi will be 0 and cos of pi is minus 1. Half minus 1 will give me minus half. So it is tan inverse of 0 upon negative number, which will be nothing but, now we all know that when the real part is negative, it will lie on negative real axis, for which the corresponding omega will be pi plus pi. So when omega is equal to pi, minus pi plus tan inverse of 0 upon negative number will be plus pi, minus pi plus pi will give me 0. So when I put omega equal to pi in the first phase spectrum, I get the value of 0. But if I do that in the second phase spectrum, you can see when I put omega equal to pi, so if you want, I'll just do it here quickly. Angle of h1 of pi is minus pi plus tan inverse of sine pi is 0 and half minus 1 is minus half. So this is minus pi plus pi becomes 0. For the second system, angle at pi will be minus pi because omega is pi plus tan inverse of sine pi will be obviously 0 once again. And this time cos pi is minus 1, 2 minus 1 will give me plus 1. So real part is positive this time. Positive real part simply means that the number is on positive real axis, for which corresponding angle will be 0, and hence the corresponding phase will be minus pi. So if I now draw the phase spectrum for the second system, it will look something like this. It will go through 0 once again, but at minus pi and plus pi, it will lead toward minus pi and plus pi here. So that's the difference between the two systems. You can see that the phase spectrum at omega equal to pi is equal to 0 here, but phase spectrum at omega equal to pi is not 0, it is minus pi in case of the second system. So by looking at this phase characteristics, we conclude that if I want to define net phase change, that means phase at pi minus phase at 0. For the first system it will be 0, and hence it is called minimum phase system. For the second system, if I define phase difference angle h1 pi minus angle h2 pi minus angle h2 0, h2 pi is nothing but minus pi minus h2 0, comes out to be minus pi. Minus pi is also equivalent to plus pi. In short, the difference between the phase at pi and 0 is not 0, it is equal to plus pi in fact, and hence the system is called maximum phase system. So we have got minimum phase, maximum phase. The first system that we had started with, h1 of z, turns out to be nothing but minimum phase system, and the second system that we had considered turns out to be the maximum phase system because of the difference between the phase values at 0 and pi. Now, if you don't want to go through all this plotting of phase spectrum and then figure out whether it is minimum phase or maximum phase, we can simply look at the positions of zeros. If the zeros are inside the unit circle, which was the case for h1z, the system will always become minimum phase. And if the zeros are outside the unit circle, which was the case for second system, then the system will always become maximum phase. So that's the conclusion. Whenever you are given an FIR system, you have to find out the zeros. If all the zeros are inside the unit circle, the system is called minimum phase system. If all the zeros are outside the unit circle, the system is called maximum phase system. Now, it may happen that some zeros are inside the unit circle and the remaining zeros are outside the unit circle. In such a case, the system will be called mixed phase system.